Well, hello from the top of the school on a nice sunny day, before the rain hits at least. I'm right up here with some solar photovoltaic cells. That's right, solar panels. Now these are another source of voltage that we can study. But how is it they turn sunlight? Watch your eyes. Let's see if I can get that sun in here. Where are you, buddy? It's up there. Ooh, there we go. How is it we can take that sunlight and convert it into useful electricity using these? All right, what's actually going on? How does it relate to the flow of charge? And how are we taking energy from one form, in the form of radiation or light, and converting it into the movement of electrons? That's really the question here. And it helps with that whole future project we hope to have. Let's look into that as a voltage source. Lainey, how are you?
Good.
You're good? Okay. All right, what do you have there in your hand? Looks like you have a motor with a fan on it. What is this? Is that a solar cell? All right. So is the fan running right now, bud? Is the fan turning right now? No? All right, watch the fan, and I want you to turn your wrist. I want you to turn the solar cell until the fan turns on. Point it at the sun. Ooh, hey, there you go. Oh, it's spinning really fast. At least in real life it's spinning really fast, but because of the frame rate of my camera, it looks like it's kind of spinning slow. So, Lainey, why is it spinning? Where's the energy coming from, do you know?
The sun.
Yeah, it's coming from the sun. That's perfect.
Good morning. I thought a good way to start this talk about, wiring stuff and power would be best begun by watching this guy hurt himself repeatedly doing the simple things you should never do while you're trying to solder or do electrical work. It can be hot, it can be shocking, it can be frustrating. It's best to avoid his kinds of behavior. Today, in order to allow you to finish working on your lab, I want to talk about power, electrical power. You should have left off around question 33, and I just simply have to talk to you about the relationships of electrical power. Then, I'd like to discuss a solar project with you and give you a short Google Doc assignment. It is super short. You have to write down your name in one place or another. That's it. We won't even get on to electromagnetic induction today. So, let's just hit these. First, what do you know about power? It is not something completely unfamiliar. Matter of fact, you've probably used things that have power ratings on them. If you've ever used anything that is measured in watts, like a light bulb, the old school light bulbs and the new light bulbs, you've had a little bit of contact with something with power. If you've used a piece of electrical equipment that runs on electricity, you've definitely had a little bit of an interaction with something with power, like my microwave right here. It runs on 900 watts. Perhaps you can generate power as well, not just use it up, with something like a generator, this 12,000 watt generator. Okay, and you can actually send electrical power. So what is power? Power has to do with energy, and either how fast it's used, so consumed, or how fast it's produced. There's a couple ways we can talk about power. These two things right here, since they use power, we'll say these things electrically dissipate power, and this is a producer, all right, or a generator of power. Electrical power. So energy transfers in electric circuits determined by electrical power, defined by these equations right here. Okay, it's a great equation wheel. Sorry about the if you pick up any extra background noise. Just the byproduct of being in a house with 8 other people. 7 other people. Holy cow. Miscount. Okay. What we're interested in today is watts, power rating right here. So power is equal to voltage squared divided by the resistance of a circuit, or power can be equal to current multiplied by voltage, or power can be equal to resistance multiplied by the current squared. No matter how you do it, its units are the same. It's all about how much energy is produced or used over a period of time. So we measure it in energy per second, so joules per second, or more commonly, watts, the capital W. Okay, that's what we're going to be using, and we can hit it real quick. Let's try 2 fast problems. First one, My microwave has a power rating of 900 watts. We're on the continental US, so that means it has to be running off the 120 volts provided to my house. So what is the resistance of my microwave using those power equations? So if I were to look back through that equation wheel, I would see that resistance is equal to voltage squared over power. Voltage squared over power. All right. The voltage was 120 volts. Remember, I have to square that whole thing. That's how I convert. Divided by 900 watts. Fortunately, since it took me so long to write, I could figure that one out. Not a calculator. That's going to be 16 ohms. That's a resistance offered by the circuitry inside the microwave. Basically, remember that the resistor in the microwave is the thing being powered. That's the thing using up all those 900 watts of power as the microwave runs. So think of the 16 ohms as a conversion of electrical power into something useful done. In this case, vibrating the water molecules inside whatever I put inside the microwave. Okay, next part, finding current. That's I. There's two different ways you could find the current. There's two different equations, given the information we have. At this point, we have power, right? We also have voltage. We also have, well, we just figured out the resistance, so we have the voltage and resistance equation as well. Both of these things equal current. No matter which one we plug into, we are going to get the exact same answer. So if I start with 120 volts, and then divide that by my 16 ohms, I would get the exact same answer I would get if I started with 900 watts divided by 120. And that would be 7.5 amps of current. Okay? So that's how we use those equations, given the right information. And you're going to have something similar with your lab. You're going to have voltages that you're reading off your circuits and currents running through a resistance you know that's set up, and you can determine the power that's used in that circuit. Another one. This is using the solar panels I've ordered. If this is a 2-watt solar panel that produces a voltage of 6 volts, how much current is running into the phone charging circuit when it is in sunlight? So, assuming it is in sunlight, or looking for current, you go right back to those equations. Current is equal to power divided by voltage. And we plug in our 2 watts of power. We divide by our 6 volts for voltage. It's not a huge amount, but when it comes down to it, solar panels are not the most efficient type of power generation. They're pretty constant, and except for producing the solar panels themselves, they're a great way to gather energy because you're not paying for sunlight. But it's a really small current. Okay? There's that piece of the puzzle. So please continue the lab. Questions 33 and on that ask about power, you know to use your power equations. And that brings me to the last piece that I want to cover for today, and that is the solar panel or solar phone charging project. I'd like to talk to you about it.
Hi, I've gotten permission to bring you into the classroom for the solar powered phone charger project. It is a completely voluntary project. You do not have to do it. And I don't want to make you feel uncomfortable or like you're unsafe. So if you do not feel like coming in, it's perfectly fine. If you do, there'll be no more than 6 students at a time. We'll observe normal social distancing protocol. You'll be more than 6 feet apart, but you can have a mask. What I would like you to do is go to that Google document. And if you want to take part, look for a time slot that works best for you and enter your name in that time slot. If you want to do it and none of the time slots work, you just have to let me know and I'll set up another time. There are 20 kits to work with. I have components to make 20 of them, and there are 24 of you. Now, If you're not interested, it's perfectly fine. If you do want to work, but you want to, give somebody else what you've made, or allow someone else in the class to have what you've made, or maybe just work with them and have it be kind of a group thing, I'll figure out how to work that if that's what you want to do. Just go in, sign up where you want to on the Google Doc, either opt out of it or put your name in one of the time slots. I thought it was very important to give the opportunity to work on this. I was really looking forward to getting them for you, so if you can, it'd be great. If you can't, I completely understand. If you're not comfortable, I completely understand. Just please go in and put your name on the Google Doc wherever is most appropriate, and contact me if you have any questions. Thanks. Here's a quick introduction to our solar charging device. This is the solar charging panel. On the inside, now the box is something we're going to have to work on, trying to get that done separate. You don't have to worry about that, at least not at first. We have a battery here. We're going to move out of the way. And there is what we're actually going to be working on. We're going to minimize the number of things you have to solder to try and cut down the time that you have to put into it. But you're going to be soldering about 6 points, connecting some wires, clipping some wires yourself, and basically, doing the essential wiring and getting this thing ready to go. As you can see right now, nothing is really glowing or lighting up because I have the panel out of the sunlight. Once I move that panel over into this little spot of sun, now our box is glowing a little bit. All right, why is that? Well, power is going to come from the actual solar panel. All right, and it goes through this DC adapter and gets plugged into what's called the power boost. That's this right here. It's a large capacitor. So the power boost circuit takes the capacitor and the direct current running from the solar charging panel, and it sends the current along and actually charges up the secondary battery. It's very much like your own cell phone battery, just slightly different voltage. Every single time we transfer from one material to another, we really decrease the amount of voltage. So this is higher capacity than your normal cell phone battery. Then we store charge all the way up in here, and it keeps it until we plug in our device into the USB connector or whatever connector that works best for you. If you have an adapter for it, I have a FireWire connector and a USB that will come with the device that you're going to build, and you can store that charge and then just flip the toggle switch and you'll see that little green LED came on. That means it's actually sending power to the charging units. So now you can charge up your phone. Alright, that is our basic introduction. We'll work on the wiring first, and again I'm working on a case for it. Most likely we're going to try and laser cut something. It's just a matter of getting access to the facility. And it'll come with this weatherproof solar panel, so it's a pretty high quality solar panel. And I'm really looking forward to helping you put one together.
The assignment I'm giving you is very simple. Alright, I have linked access to this Google Doc, and I've given you the ability to edit it. All I need you to do is come in, and you're going to put your name in one of two places. The first place is either one of these time slots. The second place is right here in this box right here. So if you wish to take part, remember this is a voluntary project, like I discussed. I'm not going to make you come in, especially if you're not comfortable with it. I have 20 kits to work with, and there's 24 of you. I don't even know if all 24 of you are going to see this document, but if you would like to make one, choose the time slot that works best for you, enter your name, so everybody can see where it's been put in. I can have up to 6 people in the room at a time. I have 2 days put out there for right now. That doesn't mean those are the only days that work. If those days do not work for you, but you want to do this, you just have to tell me and I'll figure out a time. Alright, but I can have 6 people at a time working. The hour and a half I put in here, it may not take an hour and a half. We're going to have to do this in like segments where you're soldering, and then when you're building the boxes, I still have to work on getting the boxes created. But please come in. If you are not at all interested or comfortable with coming in, please put your name down here. I have to have a recording of everybody so I know where we all stand. If you do want to build one, simply put your name in the box that works best for you. You can coordinate with people. You won't be working directly next to people, of course. You will be at your own lab table, but you'll be in the room with your classmates nonetheless. So if you would like to take part in this voluntary project, I'd love to have you there. Otherwise, just put your name in the box. Thank you very much. I need to have everybody's name in by Friday. It would be great if it was done sooner, but Friday at the latest. I'll put a Thursday due date on this assignment, but, you know, people are running late. Thank you.